We'll just wait for a few minutes and then start. Okay, I guess I'll just start. Yeah, so last class we saw, right, so some examples on typecasting where we take two classes, right? So previous to that, we saw about typecasting in general, like, yeah. So typecasting in general from inbuilt data types with the hierarchy goes in this fashion, where the bool, then the character, short, int, unsigned int, long, unsigned, long, long, float, double, long, double. So this is the hierarchy order in which the precision uh, increases. Okay. So typecasting from one to the other is sort of a no loss of data. But when you go from any of these two on the left, okay, so that's decrease. So you actually lose information. That's sort of the essential idea. Okay. Then we saw about examples how one converts, let's say, integer to double and void and so on and so forth. And what will be the behavior in those cases? Okay. So one can normally convert any data type to void, that is allowed implicitly. So this another thing to remember here is about implicit and explicit typecasting. Okay. So implicitly, yes, that's absolutely allowed, and explicitly also. But you cannot convert the void pointer to any inbuilt data type implicitly. It has to be, if one wants to do it, it has to be done explicitly. Okay. So the another example that we see is about classes. Okay. So let's say that we have two class A, the name is A and another with B. A has a public number I, integer. Okay. So some value 7. B has double, okay, 9.5. All right. So small a and small b are the objects that we define for with the data types that we have here. So that will be small a is for capital A data type, as in the class A. Small b is of class for class capital B. Now we can go further and define two pointers. Okay. So this will be class data type pointer. Remember, it's just means that it's a pointer to that object. Okay. So it stores the object address. So we use the ampersand A to get the address of the object A and address ampersand B to get the address of B and store them in P and Q respectively. Okay. Now one has to be careful. So if one sets A equal to B, that throws error. Reason being, these are two different data types. Yes. But unlike inbuilt data types, custom data types, you cannot do the the implicit way of just setting values. Okay. So typecasting implicitly is not allowed. Again, explicitly is also not allowed. Okay. Reverse, if one tries to do same story, different data types, so different classes. Okay, indeed. So not allowed. Even for pointers, not allowed. But since these are pointers, you can typecast them and write. Okay. What will that actual mean? As in, does that make these pointers usable or not? That's a different story. But one can, in principle, do this. Okay. Explicit typecasting, where you convert the pointer pointing to B to the pointer pointing to A. Okay. All right. And yeah, that's it. The next example we see is for two classes, but this time we have our class B, a derived class of A. Okay. So this time we derive the class B, okay, from A. All right. So what extra thing that happens is we'll do the same A, small a and small b defined custom data type like A and B objects. Okay. Uh, Pretty much similar. P and Q pointers to the same to those same objects. Okay. Small and small b. After that, we have the void pointer R. Okay. So just a void pointer. Okay. Now we set a equal to b. Okay, this itself will be throwing no error. Okay, so implicit casting is allowed because we are setting a derived class to a base class. All right, it's sort of like we are sort of typecasting because derived classes, okay, already have, they inherit everything from the base class. Okay, so typecasting sort of is makes them like, okay, they just have the features of the base class. Okay, so this is okay, is allowed. When you do this, we could that is not allowed. Okay, so that's like promoting your base class to the derived class, and implicitly that's not allowed. Okay, and if you try to set p equal to q again, that's fine. So you can set the pointers pretty much the same way. Okay, so you can set the base class pointer, okay, p, which is the base class pointer, to the derived class. Okay, as in the derived class now is set to the base class. Reverse again, not allowed. Void pointers, yes, absolutely. You can always do that. Not a problem at all. Every time you want to set anything to the void pointer, it will happily accept it. Okay. Reverse again, not allowed. All right. Another example we see is the pretty much like the same example as in we have A and B, but and again B is the derived class of A. Okay. We have in this case a member function, a member variable for A as an integer data A called is of data type integer. Another one of data B. Okay, it's also an integer, but now it's a member of class B, which is the derived class. Okay. Small a, small b are the objects of A and B respectively. And after that, we set, because these are public members, we can just access the variable corresponding to A, and B will have both data B and data A. Okay, because it inherits A, so it has its own copy of data A. Okay, and then we can set them some values. That's okay. After that, we have some pointers. All right, which will be PA to distinguish. Just I'm calling them as PA, PB. So these are the pointers to the objects A and B. Okay, and then we access those data. All right. So we set them values and then we access them. So one expects uh, what the output to be 3, 8, 10, right? Okay. And then we set A equals to the address of B. This is allowed because B is the derived class. Okay. You can set the derived class pointer to the base class pointer and then access them correspondingly. And then we saw the output as uh, given by this code. Okay. And then we ended with const cast expressions, okay, which essentially means our variable, okay. So again, maybe I'll just go through it shortly. References is something that essentially means in the scope of that um, function parameter or whatever, the variable is sort of treated as the same thing as whatever is passed to the parameter. Okay. So here in this case, it could be a, let's say, a const integer reference. Okay. So the ref variable itself is a reference of data type integer, but also a const. So essentially, ref cannot be used to change the actual data it contains. Okay. That's sort of the idea. If it has const qualifier, we set I equals to 10. Okay. So integer I, then we make a pointer and pass the address of I to it. So now pointer P, sorry, the pointer PTR essentially contains an address of I. Okay, so pointer PTR is pointing to 10 essentially. Okay, it's pointing to an address which contains 10. Same thing, we can make a reference, okay, and refer I to it. So for all intents and purposes, I and ref can be treated as the same, as equivalent. Okay, and let's say we change ref to 9. Okay, or we change PTR dereference it to 9, both of them will change the value in the original place. Okay. So these two pretty much work the same thing. They change I indirectly. Okay. So I is the, you can imagine I to be the original variable name. Okay. And ref and PTR are two different ways of accessing the same location. Okay. All right. Now let's say I define const PTR and const reference by defining with the same thing with const qualifier. Here will be an integer pointer and here it is an integer reference. All right. And I here, because it's a pointer, I pass the address of I and it's a reference. So I just pass I here. Okay. So defined again. Now let's say I want to change the variable I. Okay. So whatever value it contains, I cannot do that directly from const reference and const pointers because they are const qualified. But does that mean that I cannot change the value of I? Not true, because I itself is not const qualified. If it was const qualified, you can never change the values, even if you use any of the further steps. Okay. So the only restriction here is that the variables that are used to refer the variable I, okay, those two variables, the PTR and reference, or const PTR and const reference, okay, all these variables which are used to refer I, they themselves, if they are not const, you can change them directly. If they are const, then you can use some different procedures. That's the essential idea. This all assumes that the original variable they are all referring to, which is I, okay, that variable can be changed. So because it is not const qualified, then hence you can change the actual value it contains. Okay. All right. Now let's see how we change the variable which is referring to I if the variable itself is const qualified. Okay. So what one can do is in C++, you can do a const casting. Okay. Pass the integer reference as the template parameter and pass the variable is itself as the input to the function. Okay. And then you can just pass some value to it. Okay. So this essentially means it temporarily makes it non-const. Remember, it might be a little confusing to say const cast as in it's casting to const. Not true. It just means that it's casting to a non-const. Okay. It takes in a const input, okay, and then casts itself, casts that reference or pointer or anything temporarily to a non-const so that you can make changes to the variable. Okay. This will be the C++ way, and line 19 where we just typecast into integer ampersand. So that's like a integer reference temporarily for const underscore reference. Okay. So this is the C style. You can just use the brackets also to do the same thing. Okay. All right. Another thing is, yeah, as we see, if you try to change 9, you get an error because const reference is const qualified. Okay. And const pointer, you cannot dereference it, okay, because it's also const qualified. So you can't change it, like dereference and set it to 9. Okay, so these two lines will throw errors. The other thing you can do is do it in the C style way, where you have the const pointer. Okay, you typecast into integer pointer and then dereference it and set it to 9. Okay, that also you can do. That's valid. Pretty much similar to this. Okay, so you can use the C style way of doing it or the C++ style. The C++ way will take integer pointer as the template, take the variable name, pretty much the same syntax as a reference. Okay. The extra thing is that remember this is a pointer, so you have to dereference it to and then set it to 9. Okay. Now you can just print I to get the values contained in I at each of the cases. Okay. All right. So that will show that one can change the value at I through pointers and references to it. Okay. Now, those same pointers and references, it's possible that they are temporarily const so that you do not change it, but sometimes you also need to change the actual original value temporarily. So use a const cast in that case. Okay. So this is another feature of C and C++, which allows you to do the same thing. Okay. Again, remember, all this is possible only if the original value that you're trying to change, okay, is not const qualified. So if I just add here const like this, now this will work. Okay, we can actually test it out. Okay, as you see, this throws error. So because I itself is const qualified, okay, you cannot set the type. Oh, maybe I can. 11, 12. Yeah, this is as expected. And then when we have this, yeah, as you see, because the original value there cannot be changed. Okay, so yeah, that's the problem. You cannot change the value. So when you try to print I, okay, it just prints the original value. Okay, all right. So that's another thing about these templated classes. They take care of internally all these checks and other things. Okay. Yeah, that's pretty nice. Okay. Again, this is sort of what we expect. Okay. So, all right. All right. Moving on, we'll see some more examples. Okay. All right. Let's see some more examples. So we'll have the iostream header file to print all the expressions that we want. Okay. What we'll do is have a print function. Okay, which will take character pointer and call it str. So str is essentially a string, and I'm not using a string class, okay, as the like include header string, the C++ standard string. Just to show this example, I'll stick to a character pointer of string. Okay, so essentially the string will be represented through a pointer, a character pointer. So one can pass through the complete string from the starting address known through str. Okay, and what we'll do is we'll just pass this str, okay, to standard cout. So basically it just prints the full standard string. Okay, now we'll write the main function. Okay, return 0. Then we create a const character pointer C. Okay, let's have the hello world printed. Okay, at the line. So this is the const character pointer C. So essentially C is the string, okay, of type const character. Maybe I'll just call it const str. Okay, right. Next, let's say I just pass this C to C. Okay, let's say I want to print this function. Okay, all right. So any guesses what will happen? Let's say I try to compile this code.
Hello world will be printed.
Sorry, can you repeat that?
Hello world will be printed.
Yes, that's the expected behavior, but one has to be slightly notice that the const. So my bad, it's not the C. Okay, so const the str. Okay, so even if with this sorry, what the typo, but even if this one has to notice that print itself, okay, takes const character pointer. That's like a character pointer. But what we're passing is const. Okay, it just expects something and we're passing something else. So we can confirm this now, but it will throw an error actually. And that's okay. So go to the other folder. Just a second. Yeah. I'll just try to compile this now. Yeah, so that actually is the expected behavior. It actually throws error that it cannot find a corresponding function print. So essentially, if you think about it, it expects specifically const character pointer data type as the input, but sorry, character pointer data type as input, but what we're passing is const character. Okay. Ideally, yes, that's the expected behavior, that it will just take const character, hello world, and print it because stdc out just takes the whole string. Correct. That's actually the actual expected behavior. Yes, that's correct. But what if we want to achieve that same thing, but without having to worry about this not having a const input data type? As in, we have to overload this function, let's say. So basically, write this function and put const to it. Okay, so now we have two definitions of print. Okay, with one without const and one with the const. And let's say we are trying to print compile this. This compiles perfectly fine. Okay, it prints hello world. Okay, and percentage is basically the behavior of ZSH shell, which terminates the terminal. Okay, so hence that also prints here. So don't worry about it. Essentially, that's how, because we do not have an end character here, right? So that's sort of the idea. In any case, the problem then happens is you have to have overloaded functions for all these cases. Okay, so whenever you have anything with const, you have to have a equivalent function with the whole body completely. Okay, just change to const the type parameter. Okay, seems a little overkill, don't you think? So because of this uh, nature of C++, this actually C++ actually demands this, that it should have a exact um, data type passed. Like if you are calling that function exact data type passed, else it just not accepted. So to get around this, okay, so and not having to write, let's say this time it was character, let's say some other time you have integer pointer, double, and other stuff. Yes, it's possible that you might have to do different things for each data type. Okay, but having a double copy of it just with const for each of them seems like overkill, right? So there is a way around to it. What one can then do is maybe not call this exactly this way, just passing it. Okay, what one can do is uh, do a very clever const casting. Okay, where just pass character pointers, basically the data type of your variable. So this is the const string which we expect it to pass. So we'll pass. So we wanted to make it a const character. So we temporarily will make it const character pointer. Okay, and itself will pass the variable name. Okay, so it's the syntax of const cast with const character pointer taken to the template. Okay, and the input. So these two brackets. Okay, so the highlighted blue ones. Okay, so currently highlighted. That's the parameter input for the const cast function. Okay, takes the input variable const cast, and the whole thing is inside the print function. Okay, all right, and then we just end the line. Maybe I did not mention previously. Okay, so I just mentioned this. So this is C++. Style. This is the style. This is the C style. This is C++ style. Okay. So we'll use the C++ style right now to essentially perform the same thing. I commented this code so that we'll use the original definition of print with just character pointers. Okay. And here we're temporarily recasting our const string. Okay. Just to a character pointer string and using the definition print here. Whatever we have defined here. Okay. So let's compile and run that. Yeah. So nicely it prints the expected value, what we want it to do, right? Okay. So this is a very useful thing about const cast. If we want to temporarily use a definition of print like some function where we do not have a const data type for it. Okay. So we can temporarily recast that same const some data type pointer or something to a non-const temporarily using const cast, let's say, and then just use that definition. We don't need to rewrite the full complete thing. Okay. Any questions?
No, sir.
Okay, sure. In that case, just a second. In that case, let's also look at the C style of doing the same thing. Okay. So what we'll do is just have the bracket. Okay. So essentially, in C, you typecast anything with just having the same character data type or whatever data type you want within bracket before the variable name. Okay, that's it. Its syntax is pretty simple and straightforward, but the intention behind this is not exactly clear, right? As in, are you here casting a const data type to some non-const data type? It's not exactly clear. It is the same syntax for converting any data type to any data type, essentially. So while yes, this is useful and definitely easy to remember, but it can be a source of bugs and errors. And plus, it's not very, if the intention of the one writing the code is not clear. So hence the syntax of C++, where the intention is explicitly clear. Okay. So yeah, that's essentially the idea. So because the intention, once you make the exact statement, right, it leads to less errors down the road. So that's sort of the idea of writing in the C++ way of things. Okay. And this is the C style. So let's comment this and then try to print. Yeah. So yeah, again, that also prints. So you can do it in either way, either or. Uh, yeah, but that's the thing. It's not that there is a difference in performance or anything. It's just the difference of uh, notation, as in what the code writer wants to convey. Okay. All right. Any questions?
Yes, sir.
Yeah. Okay. Yeah. You guys can, if you have any questions in between, you can always stop me anytime. Another thing is, if you have questions from previous sessions or previous topics also, feel free to uh, ask. Okay. Yeah. All right. Moving on. So let's look at more examples. Uh, as usual, we'll have the IOStream header file to print stuff. We define the class A. It will have integer I. Okay. And I'll make it this as public. Again, so since I'm declaring my public portion of my class here, what will be the class qualifier for I, as in, is it public, is it private, is it protected?
It's protected and private. It's private.
It's specifically private. Okay, so if something is not mentioned, okay, so remember that is private. Protected is, yes, temporal is, it's sort of like also private for that class, but you have to mention explicitly to be for it to be protected. Okay. But, yeah, thanks. So I'll make a constructor for this. Okay, so it takes let's say I underscore. That will be my input variable. I underscore is the input variable. So the constructor will have a portion where it sets the I, taking the I underscore.
मुझे
Okay.
पीना है क्या
Any questions?
मुझे भी पीना है चाय बन रहा है
Okay, if there are questions, I'll just mute everyone. Sorry about that. Okay. All right, moving on. So we'll have a empty constructor, as in it just set some values. Okay, it's not nothing fancy. Just takes I underscore. Okay, and sets I, your internal member variable private, which is private. Okay, to that I underscore. Okay, there's no body to it. That's just not required right now. We'll write a getter function, which is const. Okay, basically means this function cannot change the variable that basically is involved here. Okay, that's sort of the idea with having the const function, const qualifier here. We'll just return I. Okay, because we don't have direct access to I outside the class, because this is a private member, we need to write sort of a getter function. So that's the get function's work here. It just returns the I. Okay, hence the data type of get function is also integer. Okay, that's another set function. It doesn't need to have any data type. It just sets value. So it will take some integer, let's say j. Okay, and then sets I equals to j. Yeah, that's it. Okay. Then we'll make a print function with character pointers. Okay, string. Pretty much same as before. We'll have the string out. We'll pass the complete string and then just end the line. Okay. Coming to the main function. Oh, sorry. Yeah. We'll make a const character pointer string. Let's call it const str. Okay. The string can be just hello world. Should I end it here? Yeah. Then, yeah, let's just print it. So directly printing it. Okay. So this we know that will throw error. Okay. Just for completeness, I'm putting this one there. The other thing to do is not have just the const my bad, const string. Yeah, not have that const string itself, but have make it like a const casting. So we'll cast it into character pointer with the const cast. Okay. So const cast string taken and cast. That would be good to go. Yep, that's good. So yeah, this should not be any. This is valid. All right. Let's print this one and see. This is essentially what we had from the previous file. This time we have some other parts to the class itself. Okay. Now let's make a const a taking, sorry, data type. The object will be a. with the bracket. So the constructor takes value 2, let's say, and A is the class name. So you have to put it as a data type, and we're qualifying it with const. Okay. So here the object itself is const. Okay. So now let's say we print the value of I in A. Okay. So to get that, we use the getter function. Okay. All right. And then just print it. So hello world is from the original print function. Now this time we have the value I from A. Okay. So we passed 2 to it. So the constructor takes I underscore as the value 2, sets that I underscore value, which is 2, to I, which is the private member. Then the getter function get returns that same I. Okay. All right. But let's say I use the set function now, and let's just set it to 5. So set function takes the value integer. So I'm just directly passing it, calling the set function on the object A, small a. Okay. Yeah. So let's see what happens to this. Yeah, that throws an error. Reason being, A is cost qualified. Okay. So changes to um, variables like this is exactly not allowed. Okay. The only reason we were able to change I was because of when it was actually created. Okay. So when objects get created, okay, this is also true on the other side. So when you have, let's say, const integer, you can have private variables const integer. To set them initially, you can set them during the construction itself. Okay, like this. After that, if they're const qualified anyway, you can't change using some setter function or anything. Or inside the class itself, you cannot change them. But during the construction, you can like set them initially. Okay. The object here being the small a, the object of this class capital A. Okay. This object is const qualified. Okay. So what it sort of does is it makes its members also sort of const. Okay. So you're not able to directly change I, okay, through a set function. So hence this throws an error. Okay. Right. So let's say we want to change uh, the value. Okay, because the originally I, small I, okay, is not exactly const, right? So how do we use const casting in this case? So let's do that. Const cast template. So this time we'll pass the template A reference, okay, because we want to change A itself, okay. So we'll pass A. So essentially this makes A as non-const, okay. Then we use the member function using the dot function dot operator. The dot set vector 5. Okay, and then enter line. So pretty much same thing. But now let's print after changing it. This one. So this will throw an error, but yeah, this will throw an error, but this line, let's see. Okay, the value is now changed to 5. So this usefulness of const casting is that it changes the behavior of a object also temporarily to a non-const. Okay, for its inter-member variable, I'm saying. So because the object itself becomes const, its member variables also sort of become const, and you cannot change them directly. Like after the construction, I'm saying. Making the object itself as non-const temporarily using const cast. Okay, I can call the set function, pass 5 to it, and change the internal variable I to 5. Okay. I hope this is clear. Any questions?
Sir, I have a doubt, like why we have used ampersand after capital A.
Right. So the reason being that I want to treat the variable that I'm passing to const. Okay. So here I have A, right? So this const cast is essentially a function. Okay. Uh, Forget the template for now. Sorry. Forget the template for now. Think of print or set or get. Okay. So we have to pass a variable to it, right? So const cast expects a variable. So that is the this portion of it, which is A. All right. So because it takes a variable, all right, how does it know that it will change that variable or change something else? As in, this comes again to the passing by value and passing by reference that I discussed last like few classes back, but I can again talk about it. That's okay. The point being, I'll maybe refer to mm, uh, okay, should have some references. Reference, yes. Yeah, essentially something like this. So let's say you have a function and you pass, so let's say void set, and it is some data type. Forget the standard integer vector. Think of it like just integer or something. Okay. And then we pass B. The other case is same thing, but passed with ampersand. So in one case, let's say I call, in both cases, I call set function pass with A. Okay. In one case, let's say this is the definition I'm using. A is passed as a reference. Okay. And in another, if I have this one enabled, okay, like this, so A will be passed as a value. Okay. So any change I make to B will not get reflected in A because it will just create a copy of B, do all the changes, and then B goes out of scope for set function. Then it just destroyed. Okay. Yeah. Okay. So that is one case. The second thing to remember here is when you pass A, in the case of, let's say, this one, okay, A gets passed as a reference. So B and A both are treated as the same thing in the whole whatever code I have. Let's say I set it to some value. Now, after this function gets over, it's done, okay, the values that are set to B will also get reflected in A because A and B are the same thing. Pretty much the same case here. If I do not pass, so here I'm through this template, instead of just saying A, I'm saying it's a ampersand as an A reference. So if I just put A, whatever changes I do to A here after passing, it will not get reflected to the actual A I have here. What will happen is it will create another copy of A. So small a. Yeah. So yeah. So the small a object that we have, that will get copy created. Okay. And to that copy, we'll set 5. But what happens is then this function gets done, right? So that value setting will not get reflected in the actual A that we have here. That's the problem. You can try this out actually. So if you try to do this, yeah, it will throw an error, of course, because A is a reference. Yeah, so that's another problem. But the point I'm trying to make here is you have to make A as a const reference. So here I'm using as a ampersand for a reference, telling the function that I want A to be treated as that A that I'm passing. I want to work with that same A. Okay, so then that same A is, okay, its set function I'm calling and then setting it to 5. All right.
Yes, sir.
Yeah. So that is the other one. And yeah, so hence this was my another example that's going to you. So this is just throw an error. Okay. Yeah, it's not a reference. So actually, essentially, const casting sort of expects a reference or a in the template as a reference or a pointer. That's you can think of it that way also. Yeah. Yeah. Okay.
Yes, sir.
Then we can go to okay, we can go to something else. Right. So yeah, I hope this is clear. So essentially, when passing parameters, one is the reference passing, another is by value. When you're passing, of course, one can also say, what about pointers? Technically speaking, passing, so let's say this was some data type with star, let's say. So essentially, you're passing a pointer, right? That's technically a passing by copy, as far as I would say, because essentially what you're doing is you're passing a pointer, let's say some A, and B is another pointer here, it's just a different name. So the pointer gets copied. So basically, it's an address, right? And then you can just dereference that address to the same location and then play around with it. So essentially, what I would say is there are only two kinds of parameter passing. One is by reference, another is by copy. The copy could be just a normal variable like this, or it could be with pointers. Okay. Right. Then, yeah, moving on. Let's reinterpret. Uh, stars. Let's see the another example of reinterpret cast. Your string. I mean, okay. So return 0. So let's say I have a long L which has the value 8. And let's say I just print this guy. Okay. Then I have another variable D. Let's say this one has some value 7.5 and a pointer to that guy. Okay, so I'll call it double pointer PTR D. So just to say that this is a double kind of pointer, that D is pass and plus and to D. Okay. Now, excuse me a second. Okay. Yeah, let's say I want to set L equals to D. Then simple. Not D. Mm, yeah, long will have address. Okay, yeah, just PTRD. Technically speaking, long can hold 64 bits, right? And it stores integers. Yes. Pointer PTRD is pointing to data type double. Yes, but the variable itself is of size 64-bit integer, as in it stores addresses, right? So addresses, at least in this machine, the default behavior is that it stores 64-bit integers. Okay, so the 64-bit integer storage size capacity of PTRD and long, which is the L, is technically the same, right? So technically speaking, this would work. I mean, this can work, right? So I have an address of D that I'm storing in PTRD. So this is fine. Just comment this. And if I try to compile this one, this is completely fine. It'll print 8. Sure. Now currently it stores 8, but now I want to reset it to some other thing. Where the value that it is actually storing is a complete address. Okay, it's the 64-bit integer, which comes from PTRD. Okay. Any confusion regarding this? Essentially, what I'm saying is the pointer variable stores addresses. That is always the case. Okay. In any uh, time, you have whatever may be the data type pointer and then the variable name. Okay. Remember that the variable itself always stores 64-bit integers. Reason being, it stores addresses. It always stores addresses of the system that you are in. So for example, you're here in general now in these modern systems, we have 64-bit machines, right? So the addressing will be of 64-bit integers. Hence, the variable will also store 64-bit integer. Then one can definitely argue, then why do we even have the data type? It just means that the address is pointing to a location, okay? And that location or the address from the starting address, how do I treat the data there? Okay, that's what is determined by the data type here. Meaning, if I have an address here, let's say 0x, some 100 or something, some hex number, some is basically the saying what the address name is. Okay, that address, starting from that address, all the values it will start reading off, okay, will be of double type. Okay, that's all what it says. All right. So essentially speaking, PTRD, the value it contains, I'm not dereferencing. Remember here, I'm not dereferencing PTRD, as in I'm not dereferencing and accessing the double value there. Whatever the address contains, I'm accessing the actual value inside PTRD, which is the address or ampersand D. Okay. So technically speaking, I can whatever 64-bit number I have inside PTRD, I should be able to write it to L because L also has 64-bit width as a size. It's a long, right? Long, you can think of it like a long integer. Okay. But if I try to compile this now, this will throw an error. Okay. So they're essentially trying to convert a pointer PTRD to some long or something. While we know that it is possible to do this, implicitly compiler will throw the error because it wants to save you. Okay. So this can be some source of errors and mistakes. So it's not exactly how to put it, default behavior of compiler to LM to just give this to you. Okay. All right. So hence, what one can do is a very simple C style of casting. Just cast it to long and PTRD here. Yeah, that's it. Instead of this, just have this. Pretty straightforward. And then it's converted. Okay. Compiler will not shout at you or anything. All good. All right. So we can also try to print this and see. So we'll print the address of B. Okay. Okay. Sorry about that. Print L or let's print PTRD itself. Okay. The another thing one can do is print L. We expect them all to print the same thing. Okay, so as you can see, so this is a hex number or representation of whatever the address is. Okay, uh, usually yes, it's a 64-bit number, so there'll be 64 bits. Same thing, you can represent that binary number, okay, to a hex number, hex representation, right? So hence 0x. So this is the hex representation. As you can see, all three are sort of returning the same thing. Oh, okay. Only thing is, L is different here. Okay, it's not represented in the hex representation, but I think yeah, that's represented in binary. Yeah, probably, or decimal. I think it's decimal representation. Yeah. In any case, reason being that the actual bits that we copied, okay, that is exactly the same. So I just treated that pointer D as a long integer, okay, and then stored it in L, right? So if you think about it, yeah, there is some typecasting happened here. Okay, so hence it's printing it this way. But the essential idea that I wanted to bring to attention is PTRD contains 64-bit integer. I should be able to write it to a 64-bit integer. Okay, that's the idea. Implicitly, not allowed. Okay, compiler will shout at you. You can do it explicitly by a conversion. Okay, now let's look. So this will be the C style. Okay, of typecasting. Let us look at a at the how C++ will do it. Okay. It's called reinterpret fast. Okay. takes long as the template type. And again, like pretty much similar to const casting, it takes a parameter. So the parameter is just passed as ptrd. Okay. And then let's say we print L. Okay. Yeah, that's it. It's exactly the same thing. It does the same type casting. Okay. All right. So the same bits are there, but it's sort of like treated now as a long integer. So it will treat those same bits as an integer and show it to you. Okay, that's hence it's not written in a hex representation. It's written in a decimal representation. Oh, so that, and then the other thing you can do is, oh yeah, the useful thing I'll definitely I should notice you can take as in you can always print the size of your inbuilt data type to confirm what it is. I did say it is 64-bit or whatever. You can actually check it. So let's say size of long, okay, is you can use a size function, size of size of then long, just print the line, okay, and print it. Yeah, it will print as 8. Okay. Oh yeah, it returns in bytes. Okay, so 64 bits is 8 bytes. So it prints 8. So long can store 8 bytes. Okay. Uh, any questions?
Uh,
Hmm?
Reinterpret is a keyword.
Reinterpret cast is a function. You can think of that way. It's pretty similar to like the get function, set function, the main function, anything with a return type. Yeah, it returns. You can treat it like a function.
Okay, sir.
Yeah, without it doesn't. It's not there in some namespace. That's it. It's currently yeah, okay. STL doesn't. It's not there in the STL namespace. It's just there in the C++ nameless function. You can think that. Yeah. It's also a function. Uh, Now, one can definitely ask if C style is so simple, I can just do it this way. It works for const, it works for this reinterpret cast, it works for, we will also see static casting. Sorry, my bad. Yeah, sorry. Yeah. So there's a reinterpret cast, so it works for this thing works for interpret cast, const cast, and I think we had some other type. So essentially, every form of typecasting has the same syntax for C. The reason being to do it in C++ is that intention. Again, it makes it clear that here we are doing a const casting, as in explicitly say that, oh, this is my const type, data type pointer. Here I'm making it non-const temporarily. Please don't shout at me, Mr. Function, right? That's the intention here. Okay. The another intention with reinterpret cast is that we are again reinterpreting whatever variable we had. Okay. Uh, oh yeah. Okay. Whatever variable that we had wanted to pass, which was actually a double pointer. We want to reinterpret the same data type, okay, as a long. So here it means that we want to make it a, we want to reinterpret that. So the intention is more clear. Okay, so that's the sort of the idea. And yes, one can just think of all these functions, reinterpret cast. Again, size of is also a function. Okay. Um, you can treat yeah, const cast also as a function. Okay. Essentially, they're templated functions. So we haven't talked about templates, but they have another piece. It's like with this single angular bracket, they take some thing. Okay, that's called a template. And they have this usual part of functions, which are small braces. So they take parameters. They take the variable. In this case, it takes the variable here. And in this case, also it takes the variable. Okay. I pass the long data type to whichever I want to reinterpret to. Okay. Here I wanted to reinterpret as long, so I pass that as the interpret type. Okay. Yeah. Is that clear?
Yes, sir.
Okay. 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 Moving on. Study casting. I have the main function, then define integer. Let's say I is 7. Okay. We'll define a long, which is 10, let's say. Then double variable d, which will be, let's say, 7.5. And yeah, if we print I, so we know what to expect. We'll print 7. That's um, straightforward. Okay. We saw this before, the first one. Okay. In typecasting 1. So moving from one data type to another. Okay. So one can use this C-style way of explicitly typecasting. We'll pretty much see the same thing when how to do it in C++. Okay. So let's say I write I equals to D. Okay. So here I'm converting a double to an integer. So this is implicit typecasting, but I also lose data. Okay. Why is that? If I say, why do I say I'm losing data?
So it will show an error.
Not exactly. It will compile perfectly. But what I'm saying is I'm actually losing data here, but losing precision will be more precise. Say. Okay, so the reason being double is of 64-bit data type. Okay, integer is 32 bits. In no way you can squeeze one to the other, sort of. Other than that, integer will definitely chop off the fractional bits. Okay, so it cannot represent 7.5 anyway. Okay, so it will represent 7 anyway. 7 to it. Okay, actually maybe I should not make it 7, and maybe make it 2.5. Okay, yeah. So now when D writes to I knows that it will only represent integers, right? So it will only represent the integer bit, not the fractional bit. So in that sense, you definitely lose precision. Okay, just so happens that D represents this 2.5 in 64-bit format, floating point representation. Okay, I represents the same number using 2's complement uh, method. So just so you guys remember, integers in computers are represented using 2's complement. Okay, they could be, so integer is 32-bit, so it could be 32-bit representation, 64-bit or whatever. But for integers, it uses 2's complement. For double float and this floating point data types. Okay, they are represented using floating point standard. That could be, and again, that itself could also be 32-bit, 64-bit, or whatever. Here, double happens to be 64-bit, okay, because of my machine. So hence, this 2.5 will be represented in 64-bit floating point standard. Integer I will be represented in 32-bit 2's complement standard. Okay. Okay, moving on. So I equals to D will have an implicit typecasting. Okay, so that's that. Then same thing, I can just do a explicit typecasting. So this will be the C style. Uh, C style typecasting. Now let's look at how we do it in C++ way. Okay, so you have a static cast, pass integer to the template, and D variable, right? So yeah, this. Pretty much the same thing, just that is C++. And if I try to print I, now should show me the result. So initially it had 7. After getting 2.5, and again reinterpreting, I wouldn't say reinterpreting, it's more like static casting, it's typecasting proper. Okay, so that will be 2. All right, so the slight difference is that when it's static casting, there uh, yeah, so when you're using static casting, it follows the rules of type conversion, as in promotion from low data type to high data. When I say that, it will be like 32 bits to 64-bit or 64-bit to 32-bit, changing from one floating point representation standard to another. All those things are taken care of in your static casting. Okay. Reinterpret cast just reinterprets the same bits exactly to some other thing. Okay. So it essentially means that I have a string of 64 bits. Okay. I'll just interpret the same bits as maybe a double. I can do that as maybe a 64-bit long integer. I can also do that. It's up to me to how to interpret that string of numbers. That's what reinterpret cast does. Okay. What static casting does is it converts the actual number. Okay. So the bits are something. Okay. So actually, if you think about it, the bits change. In D, there was a string of ones and zeros in some particular order. Okay. Which meant 2.5 in decimal in 64-bit representation of floating point numbers in some standard, let's say. Now the same bits mean 2.5, yes. So what if I want them to be stored in I? Okay, so it is stored 2. Now 2 and 2.5 have different bits altogether. All right. So now if you try to print the actual string of ones and zeros in I, they will look completely different than ones in D. Right. So this is what static casting does. It casts numbers, okay, from one to another, sort of trying to preserve the actual value itself. Okay. Reinterpret cast does not change the string of uh, ones and zeros. It takes the same thing, reinterprets as a different thing altogether. So what I'm trying to say is, if PTRD contains a string of ones and zeros in one representation, let's say 2's complement, it might say 2 billion or 2 billion or 247, let's say. In floating point representation, it could mean 6.5, let's say. The same string of ones and zeros. Okay, so remember, that's the difference. Reinterpret cast does not change the string of ones and zeros. it just reinterprets it all differently altogether. Static cast does. Okay, I hope that is clear. Okay. All right. Okay, so I try to print B. So I think the expected is you have to find no worries that same thing will have for like whatever we did for I, we'll just do the same thing. First, just interchange D and I. Here's D, here's double I, D, double I. Okay. Now if I try to compile this and print, so 2.5 is the original value. If I try to have 7 right in it, so it will just have 7 expected. So that's the implicit typecasting. Then if I have explicit C-style typecasting, again that's expected. It's same behavior. Same thing. I can do a static casting in the C++ type. I just have to say what I'm trying to convert to. So I'm converting it. So this function is overloaded, as in it has many definitions of what it can take. So it interprets that it will take an integer, okay? And the template says to convert it to a double. So it will do its best accordingly, okay? Then if you try to print it, it's the same. Okay.
Yes.
So before, change, after, before, change, after. All right. So I hope this is clear. Right. So 1. Let's make it 2. Another example. So write the main function. I, let's say, has 5. Long L has 12. Uh, double, just let's say 3.2. Then I'll have an integer pointer and call it PPRI. Stores the address of I, a double pointer, PRD, stores the address of the void pointer, PPRB. Okay. Yeah, this I'll just leave it for now. I don't need to actually store anything because it's a void pointer, so I can do it anytime. So I can have ptr equals to, let's say, ptri allowed, and this is also allowed. So this will be implicit typecasting, where we are converting one data type pointer to void. So void will accept anything. Not a problem at all. Right. So that's the thing about void pointers. This is just not thrown error. Like, we can just check it also. So this will be yeah, doesn't throw error. All good. But what if I have reverse, right? So let's say this equals to ptrv, and same goes. It's try to set I and D, which are integer pointer and double pointer, to void pointers. Like use void pointer to set them as integer pointer or double pointer. This will throw error because implicitly you're not allowed to do this. All right. So C++ doesn't allow implicit type conversion from void pointer to any other pointer. Does that mean it's not allowed? No, that's not true. It does allow you to do it, but you have to be explicit about it. Okay. So same PTRI. Okay.
So error is there because we have used void and it cannot return any value.
Sorry, repeat that.
PTRI equals to PTRV is wrong because void is written before declaring PTRV.
Oh, no, that's not true. So I declared them perfectly fine. It just so happens that if I have PTRI, which is an integer pointer, and PTRD, which is an integer pointer, I'm setting PTR them to PTRV. Okay. So let's say PTRI was some address. Okay. Again, it's a pointer. It has some string of ones and zeros, right? It's some pointing to some address. Now that address I can copy to PTRV. It is a perfectly valid thing because all of these are pointers actually. PTRI, PTRD, PTRV, anything. They all are addresses. The difference is that this PTRI, it points to some, like it has some address, and that address, whichever it's pointing to, right? That address starting from that starting address, we are treating the number as integer. Okay. PTRD treats that its own address, whatever it's pointing to, as a double. Void says, I don't care. I don't have any data type notion or anything anyway. So I just have addresses. That's it. So technically speaking, you can take an address, and that address, if it loses its whatever it's pointing to, this is allowed in C++. Is what I'm saying. Even C also. So PTRV happily accepts a address, and PTRI technically here loses. PTRI itself has like its own interpretation that it will be integer. That is fine. But PTRV will have the same address, but PTRV, for perspective of PTRV, that pointer address, its data type is not known anymore. Okay. But that actually provides a useful thing. This is not allowed. This is allowed implicitly. Explicitly, if you think about it, the opposite is happening. We are saying that the same address will be now treated as an integer, and it's the same address. Whatever address PTRV, let's say it had. Okay. We are saying now that PTRV will be stored in PTRI. Okay, that's fine. Peter will happily accept a string of 64-bit number. Sure. Now it's just the difference is that PTRV originally it did not know anything about the data type of that address. So there are two aspects to a pointer. One is the address. Okay, so that's what this guy stores. Okay, and the second is what is the data type of whatever it's pointing to. For PTRI, it'll be integer. PTRD, it'll be double. For PTRV, void. Void means nothing. Okay. Now, because this PTRV is like written to PTRI, it will happily accept the address. But now we are saying that PTRI must interpret that as an integer. It just so happens that C++ implicitly doesn't allow you to do this. But I can always take a address and read off of data as however I want. I can treat it as an integer. I can treat it as a double. I can treat it as anything actually. But what C++ tells you is, yes, if you want to do that, I'll allow you, but you have to do it explicitly. Okay, so that's what you have to do. So you have to reinterpret your PTRV, okay, explicitly to integer pointer, and then you can store it to PTRI. Now, does that, when we do this, does it actually make sense or not? That's a different story altogether. As in, if you read off data, do we get garbage values or not, or some real values? That's a different thing altogether. We'll not worry about it. The point just being, let's say I have some address. I can always store it in some other pointer. Pointer V will have some address, right? I'll store it in my pointer I, but because it was originally a void pointer, I have to typecast it explicitly, okay, to integer pointer and then put it to inside PTRI. Okay, so that now PTRI knows I'll get some address and explicitly now that I am treating as integer pointer. So Peter I is also happy, and the compiler is also happy. If you try to compile this code, yeah, this will be completely fine. Yeah. Same line, but it's just that you can't expect it to implicitly do it for you. You have to do it explicitly. That's the only difference. Okay.
Yes.
Yeah. So this is the C style. We have so this one was like seen before example also, and pretty much similar thing we have to do with here. We have to just change here to double. All right. Okay. Now let's look at how to do the same thing in C++. Wait. So pretty much same thing, but this time we'll have static cast, change it to integer pointer and pass the pointer to it. Yeah. Instead of integer, double. So what we're saying is take the address, now treat it as a integer pointer and then store it in PTRI. Same with here. We have some pointer. It's currently it is a void pointer. Take that address, treat it as a double pointer and store it in PTRD. That's it. So if you think about it, in this static casting, the bits actually change. Okay, so P, there was some string of bits, like let's say it was 1 1 1 1 1. When it was interpreted as an integer, okay, so that new I might have 0 0 0 0. Just an example. Let's say in pointers, yes, something sort of similar could have happened, but it actually doesn't. Peter V will have some strings, right? Some 0 0 0 0 1. Okay. Peter I will also have the same exact because they actually point to the same address. That fact does not change. Just the fact that PTR-V, whatever address it was pointing to, the data there in that address, okay, it was of no known data type. It was just void. We are just treating it as an integer. That's it. Okay. So here currently for static casting for pointers, it sort of acts as a reinterpret cast. You can think that way also. Okay.
Yes.
All right. Okay. With that, I sort of covered the topics that I wanted to cover today and discuss. If you have any questions, you can feel free to ask. Next class, I'll be uh, covering. Let me just see. Yeah. We'll talk about templates. We'll talk about class templates. We'll talk about some operator overloading and so on and so forth. Some things about polymorphism. Yeah. So those will be the topics next class. Okay. So templates I can probably start from next time. Yeah. Yeah, let's yeah. Okay.
Yes.
So yeah. That's the thing. And the other thing is again, this what I give advice to in every class. Do practice. So all these concepts of modern C++ and other things, they might look a little daunting at first when you encounter with all the syntax and why do we need to write this and all that those things. Once you keep writing these things, it becomes more familiar and easier to understand. The best way, what I prefer is write the code, make changes like this, and then just try to compile, see if it throws an error. And compiler is pretty good at it. So if it sees an error, it will shout at you, tell you the exact same thing, and then you know, okay, where did you make the mistake? So learning by doing is the approach, just what I prefer. So hence I encourage, please do practice these things. You can and all these examples I discussed will be available in the G Drive. So that link is shared with you guys. If not, do let me know. So I'll update this today's codes also in the same G Drive link, and the lecture will also be available in the YouTube link. Yeah, so you can feel free to go through it. And yeah, if you guys have any questions, feel free to ask, or we can make it within the process. Yeah.
So where is the G Drive link? Like I'm unable to find it.
Oh, okay, I'll just share it in the chat. Yeah, just a second. So NPTEL actually shares with you, I think, Google Excel sheet or something. I'll share the link. No worries. Um, so this is the G Drive link, and I don't have the playlist YouTube link. Let me see if I can get the playlist itself. Just a second. So this one is, or yeah, I think this is the one. This is the playlist for all the lectures that I covered. So it should have, I think, till 7. Yes. So the today's one, which is the 8th week, I'll also upload now after the class. Yeah, feel free to go through them. And yeah, if you have any questions, yeah, you can ask me any class. Yeah, anytime. Okay. See you guys in the next class.